All right, so when we talk about derivatives, the first thing we have to do is we have to define what's called a secant line, right? So a secant line, when we talk about a secant line compared to a tangent line, a secant line is a line that locally intersects a curve in two places. So I've got this blue function, call it f of x, that continues along, and there's no reason it doesn't, I don't know why it's not continuing here, but it would, it might just continue along. And we've got this red secant line that intersects the blue curve in these two places. Now, why do we say, why do we say locally there? Because when we say locally in math, we mean where we're interested. It's possible that we could have some function, for example, that does something like, this. Oh, come on. So if I've got some function that winds around a whole bunch, it might be, for example, that I want to find the secant line from A to B, so from there to there. And so there are the two intersections I'm interested in, right? Now it turns out there's this other incidental intersection over here, but we're not really concerned about that one. We're just concerned about these two, right? So that's why we say locally. There might be other intersections, but we're not really focusing on those. Okay, so what a secant line does for us then, if a secant line intersects a curve in two places, we can form a slope triangle based on those two intersections, right? So if I've got an intersection there and an intersection there, if we look at this slope triangle, well, that's not a very vertical line, is it? This is our change in y, right? That's our rise. So we could call it change in, y is really f of x here, right? Well, we'll call it change in y. That's change in y, and that's change in x. And we could define the slope of the secant line based on that slope triangle. What that ends up giving us is a really important quantity. It's called the average rate of change, right? The average rate of the change of the function over an interval is just the total increase in y divided by the total increase in x. So the change in the function divided by the change in the input. So that's what a secant line does. The slope of a secant line always gives us back average rate of change. Okay, so for example, it can be useful to us, like if we're talking about a car traveling an average speed of 60 miles per hour and is traveling 150 miles. Well, that would take 2.5 hours, wouldn't it? If we're traveling at an average speed of 60 miles an hour, we're going to go 60 miles every hour, so it's going to take us 2.5 hours to go 150 miles, right? Everybody good with that? Okay, but does that mean that the car is necessarily traveling with its cruise control on the whole time, going exactly 60 miles an hour? No, it doesn't, right? The journey might be much more complex than that. It might be that the car is, it's changing speed frequently. Maybe it's doing something like that, where the speed is changing all the time. And if we're looking at a position versus time graph, let's go back to our discussion. It's been a while ago now, but go back to our discussion of kinematics, right? Position versus time is related to the velocity versus time graph through the slope of the function, right? The derivative of x with respect to t, which is what we're going to be talking about, really ends up relating to the slope of the function, and we'll get to that in a second. But if I were to look at tangent lines to the curve at any of these places here, they represent the slope of the blue function. That's a strange concept, right? The idea that a curve, something that's not linear, can have a slope. Can it really have a slope? Well, I mean, yes and no. A slope is really a function of a line, a parameter of a line. But if we look at the tangents to the curve, they represent how steep the curve is at a particular value, right? And so the slope of the position function is equal to the velocity of the object. Okay, velocity is equal to the slope of the position function, right? And so the velocity is changing here. At some places it's not going as fast. At other places it's going pretty fast, right? But the result is that we cover a distance of 150 miles in a time of 2.5 hours, right? And one way to summarize that journey is just to say that the average rate of change of position, which is the average velocity, is equal to 150 divided by 2.5. And we can see that with this secant line. Right? There's the secant line connecting those two values. Does that make sense? What we're talking about, everybody? Okay. All right. So so let's go back to this page for a second then. So then how do we, what's kind of our quote-unquote formula for writing the average rate of change or the slope of a secant line? Well, if we look at this slope triangle, change in y over change in x. What is change in y? Let's look at these two ordered pairs. This ordered pair has an x coordinate of x and an output y coordinate of f of x, because this is just the function f. Okay? How about over here? Well, if we increase our x value by an amount delta x, then the new x value, so if this is x, then this value right here is x plus delta x, right? We just increased x by delta x. So that's our new input to the function. The coordinates of this point, this red point up here, the input is now x plus delta x, and the output is just f of that input. So it's f of x plus delta x. Okay? Presumably when we're actually in the business of calculating some derivative, some derivatives, we're going to know what x is, and maybe we're going to know what delta x is, right? If we're finding average rates of change. Like this could be, x could be, for example, 0, and delta x could be 2.5 hours. Okay? So then delta y is just going to be the change in the output. So f of x plus delta x, that's that y value, minus f of x. The difference in the outputs is the change in y. Okay? Divided by, well, we already know that the change in the input, we already called that delta x. And so this is a really important idea for us. The slope of a secant line, which represents average rate of change, is just what we call the difference quotient. It's so important we give it a name. Okay, so let's try this. Let's actually, I'm going to skip through that page. Let's just try something like this. We're given a function, a position function here in this case. So let's find the average velocity of the particle between 2 and 5 seconds. And let's remind ourselves about the relationship between these quantities, right? We know that average velocity, I'll write it with a bar. So there's average velocity is just equal to change in position over change in time. Okay, that's the definition of average velocity. Okay, so let's see what happens here. We've got our difference quotient. Instead of f's, we've got s's. Instead of x's, we've got t's. So what is going to be the average rate of change of position then? How am I going to say that? Instead of, we're jumping back to this idea. Change in the output over change in the input, right? But this time, instead of the function being called f and instead of the inputs being x's, the function is called s and the inputs are t's. So what is that? What's going to go on top of the difference quotient then? And let's write it generally. And then maybe we'll plug in numbers in a second. S of, okay, t plus delta t, okay, minus S of t, right? Does that make sense? Give me thumbs on that. How we doing? Okay, divided by, yeah. Everybody buy that? Okay, so for us, what's t? Okay, it's going to be 2, isn't it, right? That's our starting value. And what is delta t? How much are we increasing the input by? Yeah, by 3, isn't it? So, because that's 5, right? Okay. So then what's that give us? It's giving us S of t plus delta t. We could plug in specific values now if we wanted to, right? So we could do something like, we could say 2 plus 3 is 5, so S of 5 minus S of t, which is 2, divided by delta t, which is 3. Okay? And that's going to give us our average rate of change based on this function up here that we have, right? Okay, so Gabe, what's that gonna end up being? What is S of 5? It's gonna give us some big ugly number, isn't it? We're gonna get, ooh, it's gonna be a little bit ugly. We're gonna get 25 times 1/2, so that's just 25 halves, minus 5 plus 1, so that would be minus 4. So we'll just leave it like that for a second. 25 halves minus 4 is our S of 5, right? Okay. How about S of 2? That's going to be a little bit easier. 2 squared is 4, times 1/2 is 2, minus 2 is 0, plus 1 is 1. Did I do that right? 1. Okay. Divided by 3, and so that number, that's our average rate of change. That's our average velocity right there. What's that give us here? If we subtract 1, we get a minus 5. And then the easiest way to probably simplify this, let's use our trick where we just clear fractions top and bottom. So what would I need to multiply through the top and bottom? 2. Okay, good. 2. Everybody agree? I'm going to multiply through 2. Come on. There we go. So on the top, if I multiply the 2 through there, this board is just about done. Cancel the 2's, so I get 25 minus 10 on the top, divided by 6 on the bottom. So 15 over 6, which reduces to, what's that going to be? Divided by 3, and I get 5 halves. So there's our average velocity, 2.5. Okay? Give me thumbs. How we doing? Okay, good. So what's maybe even cooler than that, though, is let's not worry about finding the specific, let's not worry about these specific times. Let's see if we can just come up maybe with, with a, nah, I'm not going to do that yet. Never mind. I'm not going to do that yet. We'll hold off. We'll hold off on that. So there's our, if we want to look at maybe a little picture of that, what did we just do? Okay, so we've got this function, S of t, which is, it's a parabola, right? It's quadratic. So there's the red function corresponding to S of t. And what did we do? We just looked at the slope of the secant line connecting the function at 2 and 5, right? And what did we end up with that? If we do all that stuff, we got 5 halves for our derivative. Not our derivative, sorry, our average rate of change. don't want to use the word derivative yet. We're not there. Okay, we good? Give me 1.5. We all good on that? Okay, all right. Okay, I'm going to rather than do this example, I'm gonna do a slightly different one. Okay, just to introduce us to the idea of instantaneous velocity. Okay, so we'll just talk through a different example here. Let's say you're driving to Hermiston. Okay, Hermiston is, let's say where you're going in Hermiston is exactly 30 miles away. Okay, if it takes you a half an hour to get there, what's your average speed? 60 miles an hour. Everybody agree? Okay. When you're going by Rue Elevator, right, that little grain silo off on the right there, you know, does that guarantee that your speed is going to be 60 miles an hour when you go by Rue Elevator? Not at all, right? Okay, what could we do to maybe get a more accurate estimate of what the speed is going by Rue Elevator? Okay, what if we took a smaller interval? What if we took between the, like there's, you know, we got those mile markers on the freeway. What if we took the mile including Rue Elevator and it took us a minute to go that mile? What's that tell us? 60 miles an hour. Okay, would you have a little more confidence maybe in that 60 miles an hour as a representation of your speed going by Rue Elevator than the 30 miles divided by half an hour? Wouldn't that be a little better estimate probably? Well, if we wanted to get even more accurate, what would we do? Cut it down even more, right? What if we cut it down to a 100-meter stretch, right, surrounding Rue Elevator and did that, calculated that average? That's probably pretty accurate. If we cut it down to maybe a 10-meter stretch, you know, then it's even more accurate. How could we get it to be exact? What if we took a limit, right? What if we took a limit as the time or the distance over which we were calculating this average approached 0, right? That would be effectively, that would be the instantaneous speed, and that's actually kind of what your speedometer does. It does it in a mechanical way, but that's sort of what your speedometer does when you read the speedometer on your dashboard. It's taking very short samples of the distance you're traveling divided by the time you're traveling, and that's how you get the instantaneous speed, right? So then, if we wanted to come up with an instantaneous speed, we could take this idea of maybe, or like a instantaneous speed being like, if we go back and look at a quick example here of, if we've got this journey where we are traveling from here to here over a distance, I think this is when something was falling. We're measuring how far it's fallen. If this is its position function, there's S, right? This is represents its position after 1 second, and this represents its position after 3 seconds. The average rate of change there, the slope of that secant line, is a representation of, you know, it's an estimate of the instantaneous speed, but it's just not very good because the interval is pretty wide, right? If I were to trim that down, so we took a much shorter interval, what happens? I've got a good, I think we can do it on here. Let me just pull this one up. I'm going to use this guy. Now watch what happens here on this. On this Desmos file. Okay, we've got this function. Scoot it up here a little bit. If we're going to set the value of A to be 2, so that's where we're going to end up. We want to estimate what the instantaneous rate of change is, you know, based on the average rate of change, starting at A and increasing by an amount. I'm calling it H instead of delta X. Okay. Look what happens when I change the value of H. If I make the distance between the points smaller, what's happening to that secant line? It's starting to look more and more like, what kind of line is that starting to look like there? That's not a, I mean, a secant line is a line that connects the function in 2 points. What do we call the kind of line that intersects the function at only one point? That's a tangent line, right? Tangent line is the line that intersects the function at exactly one point. If we draw these points closer and closer together, the secant line starts to look more and more like a tangent line. Now it disappears there because look what I've done. I've got this average rate of change, and I'm dividing by h. If h is equivalent to delta x here, right? So it's the horizontal distance between those 2 points. If h goes to 0, I can't divide by 0, and all of a sudden that average rate of change function is undefined, right? So that's not going to work. But in calculus, we have a trick, right? We have this trick of taking a limit where we don't actually get there, but we could just approach that point with infinite precision, right? We'll get infinitely close. And in effect, it means the same thing, right? If I take the limit as the separation between those 2 points that form the secant line, if that separation goes to 0 in the limit, I am discovering what the slope of the tangent line would be. And the slope of the tangent line, I'm just going to draw the tangent line. There's the actual tangent line. I want you to notice something. If I zoom in on this function, you can kind of get an appreciation for why the tangent line represents the slope of the curve. If I zoom in really, really far, remember the purple is the tangent line and the red is the actual curve. What do you notice if I zoom in really far? What happened to the curvature of the function if I zoom way, way in? Flattens out, right? In the same way that, you know, we're standing on a spherical planet, but if you go stand out in a wheat field in Pendleton, you'd be hard-pressed to convince yourself of that because the horizon looks absolutely flat, doesn't it? How come? Because we've zoomed in so far on the surface. We're so close to it. If you zoom out to the moon, you can block the Earth out with your thumb, right? So it's you know, there you can see that curvature, but zooming in like this, that's, you know, it makes that curvature disappear. And if I go back to reality, you can see then that that purple line really does represent the slope of the function. So that's the purpose of a tangent line, right? Where we're going with this, and we'll get back to this, you know, just do what you can. I'll put the assignment up there, but we'll get back to this after Thanksgiving. What we're going to do with this then is we're going to use that secant line to develop a way to find the slope of a tangent line, which is hugely useful to us in math and science, okay? That's what the derivative, we're going to call that, and that's where we're going next.